Hi class, welcome to this week's lecture, which will be on deep generative models. Now in the past class we've looked at how to extract patterns from data. Now we're going to take it one step further and see how we can use this to actually generate new data. So we actually come from supervised learning. We get a data set which consists of both data and the labels, so x and y, and we learn a function to map this data x to the label y. Now in our case we've used logistic regression as this function, we've used neural networks as a function, but it can really be anything. Okay, so this can be used for classification, object detection, etc., etc. Okay. Now we're moving more in the domain of unsupervised learning. Now you're probably all familiar with clustering, right? In clustering you have data and you're trying to find groups of data without knowing what the label is that separates them. So in this case, we only have data, we don't have labels. So we need to learn the hidden or underlying structure of this data so that we can then take it one step further and generate new data. So our goal here is we take our input training samples from a particular probability distribution, and we're going to learn a new model that represents that distribution. Okay, so we can do this for two main goals. One would be density estimation, whereby we have a bunch of samples and we're trying to estimate where the data comes from. Okay. Or we could do sample generation, whereby we have a bunch of input samples again, and we have a probability distribution of the data, and we want to come to such a model that generates samples that the probability distribution of the model is very much like that of the data. Now, whenever we have a data set, we may not actually know the true distribution of features, because some certain features might be overrepresented or underrepresented in our data set. Okay, so let's say we have a data set of faces. Okay. In this data set, there is a very homogeneous skin color, for instance. And if we're training a model, then our model might actually be biased towards particular instances that are overrepresented. Similarly, if we're learning features, some of those features that are underrepresented in the dataset may actually be biased. How does that work? If there's only one example of a mustache in our dataset, the model will learn that all mustaches look like this. Okay. So today we will see how we can use generative models to learn these underlying features and uncover the over and underrepresented training features in our dataset to train an unbiased classification model. Okay. So this whole issue of bias actually also comes back in popular news examples, such as I think Amazon. This is not related to generative models. I think it was Amazon who created an AI model for job interviews, selecting job interview candidates, and they found that it was biased towards particular type of person. It was like a Western name, white skin color, male of a certain age, and that was only because the human job interviewers had in the past always preferred this particular person for certain jobs. So the AI actually can only learn as good as the human is, right? So in this particular example, we're going to try to identify certain under and overrepresented features and disentangle our data set more correctly. Right, so we can also do outlier detection. In this case, we have an automated driving system, so most of the time we have a clear highway, it's sunny, maybe not always here in Singapore. There's a straight road, okay, but there can be outliers. Okay, so in 5% of the cases, maybe there's an airplane passing over very narrowly, there's harsh weather, maybe more, in more than 5% of the cases here. There could be pedestrians crossing unexpectedly. Okay. So it's important to detect these outlier cases because then we can improve our model during training. Okay. So we can leverage generative models to detect outliers in these probability distributions. So we're going to be focusing on something called latent variable models. In particular, autoencoders, variational autoencoders, and generative adversarial networks, or GANs. But first of all, what is a latent variable? Okay. To illustrate latent variables, let's look back at a parable and story which came from Plato's Republic. So it's thousands of years old. In Plato's Republic, there's a group of prisoners that were instructed and limited to watch only a cave wall only at a particular angle. Okay, so whenever objects or persons passed behind the wall of the prisoners, the only thing the prisoners were able to see were the shadows of those objects. Okay, so in terms of neural networks, these shadows are the actual output. That is what the prisoners see. But the actual objects causing the shadows, those can be seen as the latent variables, because these are the underlying factors that cause the manifestation of the shadows. Okay. All right, so latent variables are what we're going to be talking a lot about. Our first type of model, a fairly simple model, is an autoencoder. Now, for autoencoders, it's an unsupervised approach, as I mentioned, and we're going to be learning a lower level feature representation Z, which is our latent variable, that represents our original data. Oh, sorry. So we have, let's say, an image, X. It has this particular, 120 by 120 pixels, and we want to map it onto a very small representation. Okay. Why do we care about this? Because if we have a smaller representation, it hopefully condenses the important features of the image, but it is smaller to work with. It's easier to make calculations with. Now, typically, an autoencoder has this sort of, is it an U-like shape, let's say. We have different layers of our neural network. Each of the vertical blocks is a layer of neural network. And first, there's a sort of bottleneck situation that we create. We enforce the features to go to a small representation Z, and then we have the decoder that reconstructs the original image, okay, which we refer to as X hat. So how do we train this model? We don't have labels. That's fine. I mean, we don't have labels that say there's a curl, or this is a house, or this is a letter A. We don't know anything. We only have a set of images. So we're going to train a model with the task to reconstruct the original data. That's easy, because the input image is exactly the same as the output image here. Okay. So we give it the input, original image, X. We force the representation to become really small. So the important information to reconstruct the image should still be contained in the latent space Z, so that we can then reconstruct in the decoder, this purple area, to come to the reconstruct image X hat, which should, according to our loss function that's minimized, be very similar to the original image. Okay. So we're in essence minimizing the distance between the original image X and the reconstructed image X hat. So it can be a simple Euclidean loss function, or it can be a slightly more complex way of stating the loss, depending on what exactly it is that you're interested in. All right, So this causes a dimensionality reduction. The reconstruction quality is what's key here. Because autoencoding is a form of compression, we will know that the bigger we enforce this compression to be, the more loss of information there is, and the lower the resulting reconstruction quality. How do we change the compression rate, let's say? It is by changing the size of the latent space. So we have a small latent space, we'll have a large training bottleneck. Let's have a look at the example. Here we have a classic MNIST dataset of numbers. If we enforce the latent space to be 2-dimensional, pretty small, the reconstruction quality is fairly low. If we allow it to be 5-dimensional, quite good actually, the reconstruction. This is the actual ground truth that we're comparing with. So this is something that you're going to have to weigh in your problem. You can create a really small Z, really small latent space, and your compression is going to be really good, but most likely you're going to lose too much quality. If your Z is too big, the autoencoder is not really doing much, and it doesn't have a point. So you're going to have to experiment to find the proper or the correct size of Z. Right. So these bottleneck layers, smaller ones, are actually forcing the network to learn a compressed latent representation. So in this example here, it looks like there's only one node for Z. That's most likely not going to be enough. Okay. To represent an entire image using one number, you can imagine that there's a lot of loss of data here. Right, so typically autoencoders have this U-like shape, which we call undercomplete, because the code dimension is less than the input dimension. Okay. Autoencoder also stands, for something that automatically encodes data. There's no use or no need for labels. Our reconstruction loss, as we call it earlier, I didn't mention the term reconstruction loss, basically is the distance between the reconstructed X and the original input X. Right, so how does it look in PyTorch? Basically, you create the shape of the autoencoder as you see fit yourself. In this case, we have 2 linear layers in the encoder. So you do define 2 different models. I defined an encoder model and a decoder model. And in the encoder, they look exactly symmetrical than the decoder. We have 2 linear layers with a Relu activation. Okay. Notice that the output size of the encoder is the same as the input size as the decoder, and the other way around as well. The input size of the encoder is the output size of the decoder. We use a sigmoid activation here because we're sort of regressing to estimate each pixel value. Now the forward layer then consists of the encoder followed by the decoder quite easily. Like always, we can process this on the GPU. We can use binary cross-entropy loss in the case of MNIST data, so image reconstruction. And we can use any optimizer that we see fit. Okay, this is just an example autoencoder. Depending on your problem, you will use a different one. Okay. The case of MNIST still, I made the example slightly more complete. So to add here, we have same training steps in the backward step that we have. Forward step, we just calculate the loss. We get the output first of the model, and then that's basically it. We will practice this in the lab. Okay. Right, so I mentioned most autoencoders are undercomplete, meaning they have this shape that reduces the size. There's very rare cases that autoencoders could be overcomplete. In this case, the hidden code or the hidden latent representation has a dimension greater than the input. So in some rare cases, that might be beneficial. One could train any architecture of autoencoders successfully, but you have to correctly choose the size of your latent space, as I mentioned before. Depending on the complexity of whatever it is that you're inputting the network, you can try to think how many different features is it trying to entangle, is it trying to disentangle, and how many is the minimal amount of features that I need to represent this data. So it's not always best to choose the lowest code dimension. Okay, so the lowest feature size, latent feature size. We have something called regularized autoencoders that give us the ability to use a slightly larger code size, but still encourages the model to have other properties besides just its ability to copy the input to its output, to reconstruct the input. So regularized autoencoders typically have sparsity of representation. They have a small derivative of the representation. What does this mean? It means that similar images will have similar latent variables. This is very important because it means that these latent variables really are a sort of disentangled feature. Okay. And they are robust to noise or to missing inputs. Let's have a look at some types of regularized autoencoders. First one is the sparse autoencoder. Sparse autoencoders have a loss function that includes a sparsity penalty, omega z, on the code layer z. So we always refer to our code layer as z. So fx would be the encoder output, creating the latent representation, and then gz would be the decoder output, being the final reconstruction. So what do sparse autoencoders do? It adds this omega penalty function for sparsity in the code layer, so it enforces some nodes to fall away, basically. So it's typically learned to use features that will then, so latent features that will then be used for another task like classification. So this is something that is often done using these autoencoders, not just the sparse autoencoders, but any autoencoder. We have our X original input. We learn our Z, and we can use that to reconstruct. Fine. Let's take the example that I did in my research a while ago, whereby we're trying to do emotion prediction from music. First, we need a good way to represent MP3s. Luckily for us, we have a huge collection of MP3s that we can push through an autoencoder and learn great weights here and have an excellent representation of Z. Now, we're not really interested in reconstructing just MP3s. What we're doing is, if we have a new MP3 for which we want to predict the emotion, we're going to calculate the latent feature Z, let's call it Z1, and then that one we can actually feed into a neural network that does emotion prediction, positive, negative. Okay. So why do we do this? Because our emotion dataset is actually quite small. We have labels of MP3s, but maybe there are only 100 songs for which we have these labels. So for these 100 songs, we train a model that takes as input this previously learned latent representation, trains a new network dedicated for emotion prediction. So we're hoping that this latent representation Z already has some very disentangled representation than here that will allow our model to quicker learn emotion. Okay. We also have denoising autoencoders, another type of regularized autoencoder. In this case, we're still working with MNIST here. We have an image, and we start by adding noise to the image. Then we feed the noisy image as input X. We put it through the autoencoder, we calculate the latent space, etc. But we're trying to match it to the original image. Let's call this noisy image. We're trying to match it to the original image X. Okay. And if we're calculating the loss function see if the networks works well, we're going to match X, the reconstructed X, with the original image X without noise. So in essence, you're teaching this autoencoder network to remove the noise from an image. All right, this brings us to a very interesting and popular type of autoencoder, which is called variational autoencoder. It's a very strong type of, it's a very strong model that is able to very effectively disentangle different features. If we have our typical autoencoder, it's very deterministic. So we feed it Z and it calculates or estimates this new image based on these discrete variables Z. Okay. Well, it's not really a sum, but they're Z1, Z2, Z3, etc. Very discrete, very deterministic. Now, in variational autoencoders, the Z's actually are used differently. Okay. VAEs output is typically smoother because it uses stochastic sampling. Okay. So Z basically consists of two types of Z's. We have mu and sigma. Mu and sigma are seen as the mean and standard deviation of distributions. Okay. So in this case, Z is just learning, again, Z1, Z2, etc. But these are seen as pairs of means and standard deviations from probability distributions. In the decoder, what we're going to be doing now is sampling from these distributions. So it's no longer deterministic. We're actually estimating or sampling our reconstructed image. So depending on the size that you set for Z, you will have a combination of different probability distributions, each of them hopefully representing a particular feature of your original image. So whenever you reconstruct, you sample from each distribution using U and sigma as your mean. So Z1 could be mu, Z2 could be sigma, etc. of the first probability distribution, and it'll continue down the line. Okay. Right, so hopefully what you want to achieve is something like this. You feed it an image, the encoder disentangles your latent attributes, and each of these attributes represent a very particular feature. Okay. This actually brings us to very cool papers that we've seen whereby we can use these disentangled features and, let's say, set the hair color, vary the hair color from 0 to 1, and we'll see that this guy turns blonde to brown or black haired, depending on how we change this particular latent feature. Okay, so this is the ultimate test that our model is working accurately. Right, so this illustrates this concept a bit more even. We'll have latent probability distributions for each of the disentangled features. Okay. It could be for smile. Let's take the feature smile, and we'll see that in normal autoencoders we have a discrete value. Our latent space will actually learn this whole probability distribution now, because we're not just learning Z, we're learning mu and sigma. So for variational autoencoders, the encoder is sometimes referred to as a recognition model, because they're the one identifying all these particular disentangled features, whereas the decoder model will be referred to as the actual generative model. So here we're actually forcing or constructing our encoder such that it outputs a range of possible values, statistical distribution, from which it'll randomly sample to feed into our decoder model. Okay. So for anything that's sampled from these latent distributions, we're still expecting our decoder model to be able to accurately reconstruct the output. Thus, values which are nearby to one another in the latent space should correspond with very similar reconstructions. As you can see from the image here, if we sample from these distributions, we might get either the red dot or the yellow dot, and sampling with the red will be here, sampling with the yellow will be there, and we'll still see that these images should really mimic the input. So how do we train a variational autoencoder? So the encoder, it's important to realize that the encoder really computes a probability distribution, this time p phi, which gives us the probability of z given our input image x, and the decoder computes a probability distribution q theta, which is the probability of x given a certain latent variable. In this case, because we're calculating probability distributions, we're not just going to be having a reconstruction loss, but also regularization term. But let's start with reconstruction loss. Our reconstruction loss is actually exactly the same as before. It is the pixel-wise difference between our reconstructed and our original image. Now though, we also have a regularization term. Because our VAE is learning a probability distributions, we want to place some constraints on how this probability distribution is computed and what it resembles as part of regularizing and training our network. So the way this is done is by placing a prior probability distribution on the latent distribution PZ. Okay. So PZ is some initial hypothesis or guess of what the distribution of Z looks like. It enforces the learned Z's to follow the shape of that prior distribution. So we do this so our model doesn't overfit. We'll get to how probability of Z looks like in a second. But without this regularization, so our network may overfit on certain parts of the latent space, and basically this helps smooth out the landscape of the latent space and the learned distributions. So it captures the divergence. So our loss therefore captures the divergence between the inferred latent space distribution and the fixed prior that we've placed. Okay. We do this because we're calculating the difference between probability distributions. We use Kullak-Leber divergence, KL divergence between our prior that we set, PZ, the shape that we want this probability distribution to look like, and our actually learned probability distribution. Now, a common choice for this prior is a standard Gaussian, which has a mean of 0 and a standard deviation of 1. Why? Because this basically encourages the encodings or the latent space to distribute evenly around a center of the latent space. So whenever the network tries to cheat by clustering points in specific regions, not all centralized in one region, then the network will be penalized. Right, so if we actually calculate this factor, this difference, KL divergence between these two probability distributions for the Gaussian case, we get this. Now, how does this look like? Let's have a look at training versus generation time. We have generation on the left, training on the right. And we see that during our generation, we only look at the decoder. We sample from our Gaussian distribution for all of the latent distributions, and we feed it to the decoder to get a reconstruction of our original image. In the training phase, things are a little bit more complicated. So we feed it the original image X, goes through the encoder to get a latent variable which consists of means and sigmas of latent distributions, Gaussian distributions typically. whereby we look at the loss, the regularization term in the loss function. Then we sample from this distribution, and it goes through the decoder to then reconstruct the output, which we take the pixel-wise difference with the original image X to see if the reconstruction worked well. Okay, so both of these loss functions are minimized at the same time. All right, there's a problem here because now we have this sampling that takes place here. We can actually not backpropagate through sampling layers. Okay. So how do we train this network in practice? So the key idea is to reparametrize the sampling layer. So instead of seeing Z as sampled from a Gaussian, consider it to be the sum of a fixed vector mu, the mean vector, and a fixed standard deviation vector scaled by random constants which are drawn from the prior distribution. Okay. So the key idea is we have a stochastic node, but since we did the reparametrization, the stochastic sampling does not occur directly in the bottleneck layer Z. Let's look at it in a way that might clear this up for you a little bit. So we diverted the sampling operation to the side, basically. Okay. So now the latent variable Z is deterministic with regard to epsilon, the sampling operation. In the original form, there was an issue here because we were sampling, so no backpropagation possible. Because we split the sampling up in these three factors, Z is actually sort of considered like a bias term, so we're not going to be backpropagating through it. And that allows us to do simple backprop here. Right, and this solves our problem and makes our network trainable again. Right, so VAEs. There's a very cool thing that you can do in VAEs, which is perturbing in your latent space. So what do we mean by that? So we take one particular latent probability distribution or latent variable, and we slowly increase or decrease its value. Okay. We keep all the other values fixed, and if we do that, we can start seeing things like this. So we can sample for a range of different values for Z from 0 to 1. And we might get something like in the image here, in which basically the phase moves from side to side. So the head orientation seems to be what this particular latent variable represents. That means that we've actually disentangled an underlying semantically meaningful feature within our latent space. And this is exactly what we want to try to do. We want to try to have this unsupervised learning algorithm learn or identify disentangled, meaningful semantic features. And by doing these perturbations, we can actually discover what they represent. So ideally, we'll want latent variables that are uncorrelated, independent as much as possible. So then we can do things like in this graph here, whereby we're varying two latent variables. One is the smile on the y-axis, one is the head pose on the x-axis. So we don't know in advance what these latent variables are going to be, but it turns out that we can identify them by changing their values and seeing what the eventual output of the reconstructed image is. All right, so remember what we said in the beginning of this class. Why do we want generative models? One possible reason would be debiasing of a data set. In this case, which is a very prominent issue this month, is we have a data set of faces which might be predominantly in one skin tone. Now, the data set on the left is quite homogeneous, right? And it could lead to unwanted bias if we're going to be training a classifier on this very homogeneous data set. So what we can do is we can use a generative model to learn the latent variables present in this dataset and automatically discover which parts of the latent space are underrepresented or overrepresented. Okay. So that way we can use our latent model to create a new fair and representative data set. Right. So how does this approach really work? Our variational autoencoder will learn the latent structure of faces in an unsupervised way, just like we talked about before. And if we vary one particular z, we can actually disentangle the features already disentangled. We can actually see what the features represent. In this case, we change v and the head orientation changes of the lady on the picture. So we never told the network that head orientation might be important. It just learned it by looking at a lot of examples. Secondly, we estimate the distribution. So from looking at these latent distributions, we can estimate the probability distributions for each of these latent variables. Certain instances of these latent variables may be overrepresented and hence have lower probabilities. If our dataset has many images of certain skin colors, for instance, the likelihood of selecting an image with those features during training will be unrealistically high, which can result in an unwanted bias. So now that we've identified this, we can adaptively resample data. So the way this also works is to use the inferred distributions to actively resample data during training, which is then used to generate a more balanced data set that can be used to train a more accurate, representative, and non-biased classifier. So it's a very important application. Okay. So then when this new classifier is learned with the generated resampled data, it will hopefully result in a more balanced classifier. So, to sum up VAEs a little bit, VAEs compress representations of the world to something that we can use to learn. Okay, what does this mean? We start from a data set and it compresses it into a smaller representation, which actually has a very meaningful semantic disentangled representation. Okay. It's trained fully unsupervised, so we can reconstruct from unsupervised learning. There's a reparametrization trick that we saw that enables us to train end-to-end. So we circumvent the problem on the sampling layer. And we can actually interpret hidden latent variables using perturbation. So if we vary one of the latent variables, we can see that they actually have semantic meaning. And we can use that to generate new examples. Okay. There are some variants of VAEs, such as conditional VAEs and Gaussian mixture VAEs. We won't go into too much detail on all that, but just to briefly mention conditional VAEs. So it's all good and well that we can generate data. We just feed the network. We sample from a Gaussian distribution and some random image comes out that looks like a real image. That's great. But what if we have the MNIST dataset, for instance? Okay, great. We can sample and it will give us a random digit. But maybe we want to control which digit we generate. For instance, we might want to generate the number 2. So to do this, we need to slightly change our architecture and also feed it the input label y2 in this case, instead of only the image. So in this case here, we pass along the label y both to the encoder and the decoder. Decoder when we generate, encoder when we're training. So this allows us to then just steer the generation of the images, which makes the VAE useful for many more scenarios. So another type of generative model, GANs, not the Dutch word for goose, but GANs for generative adversarial networks, are a very popular type of generative neural network. Let's have a look at how they work. So in the case of GANs, we actually don't so much want to explicitly model the disentangled properties of our input data. We are just interested in generating new instances. So we want to sample from this complex distribution, but we can't do it directly. Right? So what we need to do is we're going to sample from something very simple, noise in the very beginning, and then we're going to learn a transformation from noise to meaningful data so that we can actually learn to generate new images. So there's a simple architecture that GANs use for this principle. So we start from noise. So we start by inputting noise into what we call a generator, generator. And this generator will transform the noise Z into a generated fake image or instance. Okay. Now there's a second part to this network, which is the discriminator. The discriminator you have to think of as a classification model. The discriminator will take a real example from the dataset, it will take a fake example generated by the generator, and it will basically see if it can classify which is the real, which is the fake. Okay. So we start from noise, transform it into fake newly generated image or data. This is really what we're interested in. And then a discriminator will act as our steering model to see if we can, if the fake images are indiscriminable of the real images. So there's these two parts. There's a generator and the discriminator. This just summarizes what I just said. So again, we have this sort of positive and negative training example thing come back, whereby our generated images are the negative training examples, and the discriminator tries to distinguish between these negative examples and the positive examples, meaning the actual images from the dataset. Right, so when our training begins, we start, we feed the generator first noise. So the first function won't be very meaningful. It will transfer the noise into something very random, which will obviously be fake. So the discriminator won't have any problem to classify this real $10 bill from a fake generated non-resemblant $10 bill. Okay. As the training steps go along, our input will start to be slightly more realistic. We have some face appearing, which we can see here too. Obviously, it's still very, very different. So the discriminator can still tell this is fake, this is real. Okay. As the training progresses, hopefully the generator will come to a point whereby the generated output looks pretty real, and the discriminator now cannot tell the fake from the real image. So that is what we want to accomplish. That means that the classification accuracy for the discriminator, in the best case, will actually be 50%, because it doesn't know which is which. Okay. So that's basically the setup of a GAN network. Okay. So both the generator and the discriminator here are neural networks. The generator output is connected directly to the discriminator input. Okay. And then through backpropagation, the discriminator's classification, so it's trying to see if it can classify between real and fake images, it provides a signal that the generator uses to update its weights. And the weights in the generator will influence how the fake or generated sample looks like. Right. So in this image here, it's summarized. We have our real images. It's just we sample from them. We have a random input noise. The generator weights transform it into a fake image sample. I'm always using images as an example because they've been so popular with GANs, but it can be any type of data. And both this real image as well as the fake image gets fed into a discriminator, which classifies if the image is fake or real. Okay. So we deal with two types of losses here, the generator and the discriminator loss. So let's look at that into a little bit more detail. For the discriminator training, basically when we're training a GAN, we alternate between training the discriminator and training the generator part of the network. During the discriminator training, we ignore the generator loss and only use the discriminator loss. Okay.
The opposite happens for the generator training.
So we start from random noise. We produce a generator output sampled from this random noise, and this output is then fed into the discriminator, which for the real fake classification. Okay. We calculate the loss from the discriminator classification, and then we backpropagate both the discriminator and the generator to obtain the gradients, and we use the gradients only to change the generator weights. Basically, the generator learns to create this fake data by incorporating feedback from the discriminator. It learns to make the discriminator classify its output as real, so it wants to fool the discriminator. So the generator loss penalizes the generator for failing to fool the discriminator. So we don't allow the discriminator to change during the generator training. In the most basic form, a general adversarial network takes random noise in its input. The generator then transforms this noise into a meaningful output, this mapping function that is inside the generator, or that's a function of the generator network. And by introducing noise, we can get the GAN to produce a wide variety of data, sampling from different places in the target distribution. So we have this alternating training. The GAN training first alternatingly trains the discriminator and the generator. Okay. So maybe the discriminator trains for one or more epochs, and we switch to the generator and we repeat this as well. As the generator improves with training, the discriminator performance will get worse because the discriminator can't easily tell the difference between real and fake anymore now. Okay. So if the generator succeeds perfectly, the discriminator will have a 50% accuracy only. This is a bit of a problem for convergence of GANs because, as you might have heard, GANs network can be a bit unstable. That means the discriminator feedback gets less meaningful over time and the network may collapse. Okay. So convergence can be fleeting and your network can perform really well, and all of a sudden it just does not perform well anymore. Okay. So it can be a bit unstable, something to keep in mind when you're training GANs. There are different types of loss that we use. I'll just talk to you about min-max loss. It's one of the original losses, but there are others that you might lose. So if in a research project you're implementing a GAN, you should have a look at what type of loss would be best for your network. The minimax loss basically has one loss function for both the generator and the discriminator, with the difference that the discriminator maximizes the loss and the generator minimizes the loss. So they contradict each other a bit. This loss consists of the discriminator output for real data X and the probabilities for discriminator output for generated fake data Z. So G is the function here of the generator. So this term GZ is the fake data generated by the generator given input noise Z. Okay. Now for discriminator, it maximizes the probability that the data X is real and that the output probability for the fake data is low. Okay, so it basically means it classifies as well as possible. In case of the generator, it has nothing to do with real data. So this whole term basically comes to zero, or it's not influenced. It doesn't come to zero. It's not influenced. So we're only looking at the last term here. It's trying to minimize 1 minus the discriminator output for fake data. So basically get a high output for fake data, hence means to fool the discriminator. So this formula derives from the cross entropy. Might look familiar to you, right? The log probability of 1 minus some output. But there can be a problem with this loss. Okay. However, sometimes this training can get stuck in the early phases because of this one term here. If we're minimizing log of 1 minus the generator output, then we can actually get really stuck. So by modifying this into a maximization problem of this, we circumvent this. You'll often see this modified minimax loss. So a very popular type of GANs is a deep convolutional GANs, which is an example here of a phase generation GAN is indicated in the picture below, whereby basically we have 1, 2, 3, 4 convolutional layers, each of different shape, and they are used to generate from random noise here. And here's some example output, fake images, real images of faces. They honestly look pretty real. GANs actually work very well. I just want to mention that in GANs we'll often see an activation function called Leaky Relu, because when we're using Relu as activation, we actually have some disadvantages. The fact that they're non-zero centered and that they're non-differentiable at 0. What does that mean? A function is differentiable at a particular point if there exists left derivatives and right derivatives, and both the derivatives are equal at that point. That doesn't happen for Relu at point 0. So that means they're non-differentiable. And to circumvent that, we can use, or we can, we sometimes get a dying Relu problem because of this. And to remedy this, we can use Leaky Relu, which basically still has a very small slope when our input becomes negative, okay, thus creating a sort of leak. All right. So similar to conditional VAEs, we also have conditional GANs because the same problem exists. If we want to generate a fake sample with a specific condition, let's say we not just want to generate a face, but I want to generate a face of a young woman who is of a certain origin, then we need to be able to place conditions. And we get a similar architecture as in the VAEs, whereby we just keep feeding the label both to the generator as a discriminator. Okay. And by feeding it the label, the discriminator will take this into account as well as the generator. The result is that we can actually now give it, these are the labels that are fed into the conditional GAN, we can tell it now to generate numbers in the case of MMIST of a particular condition. And it works fairly well. Let's explore some recent advances in the field of generative models. Okay. We've all heard of the style transfer, okay, which can come in the sense of object transfiguration. In this case, we're going from horses to zebras, a very popular example. It's not really called style transfer, but it's object transfiguration. We have season transfer, going from wintertime to summertime. Very impressive, all these examples. So in this case, we're not really generating new data. We're transforming one particular image to a different style of image, or changing an object on an image. We could go from, one of my research assistants is changing faces from frowns to smiles. It works in just as much the same sense as going from horses to zebras. I'll briefly mention two approaches, the CycleGAN and the Pix2Pix network. If you're interested, you'll find the official GitHub here. You'll find a bunch of other examples in PyTorch, actually. Now, the main difference between these two examples is that the Pix2Pix is based on a conditional GAN network, and the data is paired. That means you have an example in the original style and of the same object in the new style. Whereas in the CycleGAN, you do not need unpaired data. You could have a photo of a castle, a real life photo that you want to transform into a Monet type of painting, but you don't have a painting of that same building. So your data is unpaired. Okay. So let's have a look at these approaches. Pix2Pix, it's a conditional GAN network. So we just talked about what conditional GANs are. We give a label along with the data into both the discriminator and the generator. Okay. So in this case, we have a data set of paired data. Remember, Pix2Pix requires paired data. We have a drawn shoe, and we want to generate the paired example, a real shoe from it. Okay. So the idea is we want to go from X to Y. Okay. So this is the label that you have. In this case, we have a generator that will attempt to generate a real life example. And then we have our discriminator, which will see if it's close enough, distinguishable if it's a real example or not. The condition here is the actual original input image, X. This is passed along as a condition to enforce the discriminator that the image is still resembling the original X. So that is basically how Pix2Pix works. So it gives it an original image, transforms it. The transformed or an example transformed image is also given to the discriminator so that it can compare if it's in the same style. And while all this is happening, the original image is given as a condition to the network to make sure it's still resembling it. Okay. So in this case, the key is paired data is necessary. We could try to do it doesn't have to be images, we could try to do translations of sentences whereby we have maybe not translations, maybe sentences spoken in one accent that we want to transfer to another accent. Okay. That could be an example of paired data. The Pix2Pix architecture is basically a UNet. A UNet is a convolutional neural network that has the shape of an encoder or decoder, as we see here on the photo. We have 7 layers of encoder with Leaky Relu. We know what that is. We have 7 layers of decoder with Relu and batch norm. We're all familiar with these terms by now. Okay. The UNet has skip connections between the encoder layer and the decoder layer, which you're also familiar with what that is. It makes sure that because we have such a deep network, we don't lose information. And every now and then there'll be a skip connection which looks back at the previous layers so that no information is lost. Okay. The discriminator consists of 4 CNN blocks. Here. So this is a standard conditional GAN. So we have the same loss function as we discussed before. But there is one thing that we add when we minimize the loss between the reconstructed image and the original image. We want to make sure that the images are less blurry, so we use some type of regularization. If we use L1 regularization, basically what we do is we add the sum of the absolute errors. So that's typical L1 regularization, and it sort of boils down to the normal min-max loss with this regularization term with the lambda coefficient, as we've seen before. This is the result of the original Pix2Pix paper, and the input image looks like this, and we want to transform it into a normal image. It works pretty well. Using the original conditional GAN loss, the result is not bad. However, we find that if we introduce some regularization, the image becomes less blurry and even more sharp. So that's quite interesting. That brings us to cycle GAN, which is a similar style transfer mechanism or model which used unpaired data. So because our data is unpaired, we can apply it to a wider range of problems, whereby let's say we have an original image, a photographic image that we want to transform into the style of a particular painter. Now for each painter we don't have example paintings of those particular objects, so that makes it perfect that we use unpaired data. Cycle GANs, or cycle consistent generative adversarial networks, use an adversarial loss. It's a typical GAN. However, we couple this with an inverse mapping to enforce that it keeps resembling the original input. So let's look at this network architecture. We have our start here. We have an input image. We have a generator that generates, in this case we want to make it into zebras, a zebra image, generated image. This will be fed into the discriminator as normal standard GAN. However, what is new here is that we have an inverse mapping, the generator B to A. And this generator enforces that it becomes cyclic by enforcing that these two images are looking alike. That means that the information of it is a horse standing in a meadow still needs to be constrained, needs to be contained in this generated image B. Okay. That is very, very broadly outlined how the cycle GAN network works. Okay. So notice here that we don't need an example of how that original, how the transformed input A needs to look like. We don't. Right? We can only feed the discriminator, or we will feed the discriminator zebra images, but not this particular image in zebra style. We will, however, add this new inverse mapping, which will enforce that our input still resembles, that our generated input still resembles the original input after being put through this inverse mapping. Right. Right, so if you're interested in some other examples of cycle GAN, this really is not just images. We can also do this with waveforms, so sound networks. Note that we typically not use spectrograms for generative models. We can, but it has some issues because phase information gets lost, and reconstructing an image from, let's say, a MEL spectrogram is an unsolved problem.
After such a fall as this, I shall think nothing of tumbling downstairs.
What we can do with this example sentence, for instance, is make it seem like it's spoken by a different person.
After such a fall as this, I shall think nothing of tumbling downstairs.
So that's pretty cool. So this really goes beyond images. We can work with sounds, we can work with videos. So if you're interested in this, check out the GitHub page of the original cycle GAN, and you can experiment with it on different types of data. All right, in our lab or tutorial session, we'll experiment with all of these types of networks in PyTorch. Right.